Hi, and welcome back. In this video, we'll continue working with Value at Risk, Chapter 28. No mini exercise associated with this video, but let's get back into where we left off. We computed a portfolio's VaR using the mean variance method. It's really based on the mean and the standard deviation. And why don't we get back into the spreadsheet we were working on in the previous video. Hopefully you're up to this point where I am right here. Remember we left off computing the portfolio's value at risk, assuming portfolio returns were normally distributed with a mean of 0.782% per month and a standard deviation of 3.43. For example, that left us with a 5% monthly VaR in dollar terms of 14.6 million, right? So 5% of the time, this portfolio is going to lose at least $14.6 million in a given month during those bad months that occur 5% of the time. So that assumes that portfolio returns are normally distributed. In real life, they're not. So I like this historical data method because it doesn't make an assumption that returns follow a normal distribution. Really what you do is you compute a portfolio's historical returns and then just find, for example, the 5th percentile of those historical returns, right? Rather than assuming, oh, some normal distribution and 5% of the time, we're less than more than 1.64 standard deviations below the mean. Here we just pretty much sort the portfolio returns, find a given percentile. Let's see how that works in the spreadsheet. So to do that, what we would do is find the portfolio's return in each of the historical months in our data set, right? Or we could use like a subset. Maybe we could use the last 10 years if we think that's more representative. But let's use all this data going back to 79. So what we would do is compute the portfolio's return each month, assuming these weights, right? So to do that, right, it would be 0.4 times 4.9 plus 0.4 times 0.3% plus 0.2 times 1.87%, right? And it's really just X transpose times R is something equivalent. What we've got is a matrix of weights here. And then if you can see this is like just 1 month of data, but it's kind of like a transpose matrix of returns. So you could treat this as R transpose if you thought it like that. So to find the portfolio's return using matrix operations, I'll do it. If you want to do it some other way, you're welcome to. But using matrix operations, M mult of X transpose times R, right? So X transpose is here, right? Here's X transpose. We want to multiply that by R. And so the return in this month is transposed. So we have to like transpose it again to get it back to just plain old R. So here's R transpose. If we transpose that again, it'll get back to just being something shaped like an R matrix, right? 3 by 1 as opposed to 1 by 3. Good. And let me make my weight matrix absolute. I'll lock that because as we copy and paste down, we'll compute the portfolio's return in different months, and our cell reference to the weight matrix will stay where it should be. Good. This is doing what it wants to do. It's giving me a little warning message, but we can ignore that. So here's the portfolio's return in every month going back to 1979. And to find value at risk based on these historical actual portfolio returns, assuming these are the weights we had going back historically, we would just find for the 5% monthly VaR the 5th percentile. So we can use the equals percentile function. Exclusive or inclusive should give us very similar results since we've got a big sample size, historical sample of returns. But the first argument is the historical returns. Second argument is the percentile. This is the 5% monthly VaR. And we can see that using historical data, right, and not using a normality assumption, the 5% monthly VaR is different. And it's actually more negative. And the reason for that is that this portfolio's returns must not be normally distributed. Most investment returns actually are negatively skewed, meaning that the bad months are really, really bad, way below the mean, which we're seeing currently, aren't we, in these times. So 5% monthly VaR using historical data, 5% of the time the portfolio's return is going to be at least negative 5.4%. We could express that in dollar terms, right, just by multiplying the VaR that we found above in percentage terms times the market value of the portfolio. 5.4% of the portfolio's value translates to $16.2 million. So based on historical data, the value at risk is more extreme, right? More negative. without the normality assumption. An irrelevant question is, well, which one should I use, right? Which one's right? If I'm using this as a risk management tool, I'd probably want to be more conservative and say, well, let's use whichever one is more extreme, because if we want to know, well, what's the minimum loss in a bad month that occurs 5% of the time, I'd probably want to err on the side of being more conservative. So you can compute the 1% monthly VaR in percent and dollar terms on your own if you like as an independent learning opportunity. It'd be very similar to using the percentile function right here. But let's look at tail risk, because these portfolio returns are not normally distributed. If they were, these figures would be the same. They're not. Right? And so that's one of the limitations of value at risk. We could also estimate value at risk using simulation, simulate some portfolio returns based on some underlying distribution. Actually, if we simulated normally distributed returns with a mean of 0.782% and a standard deviation of 3.43%, we'd get results that were substantially identical to the mean variance or the z-score method that's given here. The interesting thing with simulation is when you simulate portfolio returns that don't follow a normal distribution. Right? What if we simulate data where the negative tail risk events are more extreme? That's more realistic. And in class, when we meet on Zoom on April 28th, we'll actually talk about that. So in advance of that, why don't we take a quick look at this tail risk tab. You could also find the 1% daily VaR. So here's the historical daily S&P 500 return going back to August 1980. You can see we've got just about exactly 10,000 historical daily returns. Right? Average daily return is about 3.7 basis points in this sample. Daily market return, and here's the standard deviation. Right? Given the z-value of the first percentile of the normal distribution, we could find the historical. We could find the value at risk using the mean variance method, the z-score method. We could also find the first percentile of this. I guess it would be the 100th worst return, maybe, if I'm doing the math right, because there's 10,000 returns. Anyway, we'll see that daily returns are even more negatively skewed, and we'll talk about how to adjust for that in class. So let's sum up value at risk. We've seen that these two methods that we use give different results. We can also see how it can be misinterpreted if, for example, I think, well, if I go back to this portfolio, right? If I misunderstand this 5% monthly VaR in dollar terms, I think, the most my portfolio could lose in a given month is $16.2 million. Right? That's me misunderstanding the maximum loss interpretation, isn't it? Because in reality, I would like to think more of this as a minimum loss interpretation. 5% of the time, the portfolio will lose at least $16.2 million. Right? And so the false sense of security comes from the fact that, if we're looking at 5% VaR in that maximum loss interpretation, we're really just looking at 95% of the time that aren't the worst months. Right? So you can check out some value at risk disasters on your own. There's this hedge fund called Long-Term Capital Management that assumed some things were normally distributed and used value at risk, and it came back to bite them and actually almost took down the whole financial system in the 90s. An interesting read. But in class, why don't we plan to look at tail risk and think about things that we can do to adjust for it. So thanks for tuning in to Value at Risk. We've just scratched the surface. If you've got questions, I'm happy to spend more time offline with you talking about it. But thanks for tuning in.